Hello everyone, glad you all could make it to our meeting today for our Inspired by Math Club. Today we're talking about RSA Cryptography, which is a topic in higher algebra. And so it's fairly advanced, but I think it's really cool. And so yeah, we'll take a look at it here. So first off, what is RSA Cryptography? It's a mathematically based method of secure communication which relies on some number theory, the use of prime numbers, and modular arithmetic to encrypt and decrypt messages. The encryption method uses two different keys. One of them is a public key that anyone can use, and it's used to encrypt your message. And the private key is one that you would send to your friend or person that you're working with, and that is supposed to be known only to your intended recipients, and the private key is used to decrypt the message that you send. So the definition of RSA cryptography is you have a fixed positive integer m and any integer a, and is defined as a mod m is equal to the remainder when a is divided by m. And a little note, whenever a mod m is contained within the set 0 to m minus 1. So what do you need to create your cipher? What do you need to generate? You'll need a couple things. First thing is you'll need two primes, p and q, and a positive integer such that positive integer e, such that the GCD, greatest common denominator, of e and p minus 1 times q minus 1 equals 1. And you also need a positive multiplicative inverse d of e modulo p minus 1 q minus 1. So with p times q, comma e being the public key, and d comma e is your private key. And then you'll use the equation c, which is your ciphertext, equal to m to the e mod p times q, and you'll use this to encrypt. And then to decrypt, you'll use m equals c to the d mod p times q. And C is your ciphertext, and you use the letter number table above to find your M. So that's here. So A is 1, Z is 26, and all the numbers in between have their own set number that they equal. So next we're going to look at an example here. And so to encrypt a message, we're going to use the word math, or M-A-T-H, as what we're encrypting. So m equals 13, as you see over here. A, of course, is 1, t is 20, and h is 8. And we'll just use two random primes. So we'll use p is 5 and q is 11. So that means their product is 55. And p minus 1 and q minus 1 is equal to 40. So our public key is going to be 355 after we use e equals 3. Because the GCD of 3 and our 40 is equal to 1, and E is between 1 and 55. So then we'll use our encryption cipher equation from the last slide, which is this guy, to calculate, or to find our encrypted number. So here we'll take C is equal to 13 cubed mod 55. And so 13 cubed is 2195. And then we take that mod 55. 2197 divided by 55 is just under 40. So we'll take 55 times 39, and that becomes our number minus 2197, and that equals 52. So this is your process of finding your m mod a, and so this is our m and this is our a from our definition. And so once you essentially define your value, is you divide your m by your a, and then whatever remainder is left over, you multiply by the whole number and then subtract the product of those two, and then the remainder is your ciphertext. So M13 becomes 52 with our cipher of 355. And then the next one for A is pretty simple. 1 cubed is just 1, and 1 mod 55 is just 1. And then we do the same thing that we did up here for 20. That turns out to be 25. And then we do the next same thing with 8. So 8 cubed, divide 8 cubed by 55, and find the remainder to be 17. So math turns into 52, 1, 25, 17. So pretty simple to encrypt, but as you can see, it's fairly interesting and fun. But where it really starts to get more difficult and interesting is decrypting. So we'll take a look at that here. So to decrypt the message 52, 1, 25, 17, we'll still be using P as 5 and Q as 11. So we'll still be using 55 and 40. However, these numbers aren't as important as we kind of have already figured out our numbers. So to find D, we need to find where D times E mod 40 is equal to 1. So since D times E must equal some multiple of 40 plus 1, right, because we want 40, we want our number divided by 40 to be just off by 1. So we'll try where the number times 40 is just 1, but 41 is not divisible by 3, which is our E number. So next we'll try 40 times 2, and that's 81, which is divisible by 3, so that gives us D equal to 27. And this is kind of our private key. This D is our more secretive number, and so this helps us to decrypt the message. So we'll go ahead and decrypt the same message. So we start off with 52, and so decrypting 52, we'll use our other decryption formula where we solve for the original number to be translated back to our letter, where we take our ciphertext raised to our to the power of D and then mod our 55. So here we have M equals 52 to the 27 mod 55. Now the problem is we can't just plug this in, at least if we're doing it by hand. Obviously complex computers can, but if we're doing it by hand, 52 to the 27 is too large to compute to divide by 55. If you put it into your calculator, it probably won't work unless you're using a computer. But so because it's too large to compute just straight up, we have to use a clever technique. So essentially we kind of break 27 down into its binary form. And so we'll take 52 to the first times 52 to the second times 52 to the 8th times 52 to the 16th. Because whenever we multiply, the powers add. So 16 plus 8 is 24, plus 2 is 26, plus 1 is 27. So this should add up to 52 to the 27. And so what we do is we take essentially all of these numbers, 51 to the 1, 2, 8, 16, and we kind of follow that line down. And this brings our numbers smaller so that we can actually work with it. And so the first one's pretty simple. 52 to the first power is just still 52. And so 52 mod 55 is going to be 52. Now we move to squared. So 52 squared is 2704. And 2704 mod 55 just comes out to be 9. So then next what we'll do is we'll take this 9, which is the squared number, and because squared squared is the 4th power, that's essentially what we're doing here. Is now we're finding 52 to the 4th power mod 55 without actually computing 52 to the 4th. And so whenever we take 9 squared, we get 81, and 81 mod 55 is 26. So now we're doing to the 8th power with the next one here. So Um, 26 squared is 676. 676 is mod 55, it comes out to be 16. And so now we do our final 16th power. This is our 5th iteration. And so we do 16 squared, which is 256, and 256 mod 55 equals 36. So, because our 52 to the 27th mod 55 breaks down to all of these guys. Now, what you'll notice is this 81 that we had is missing. And that's because whenever we break it down into binary, we have 1, 2, 8, and 16. Which means we're missing out this 4 in the middle. And so you might think, well, we need to add that in, but because adding in the 4 would bump our number up to 31 rather than 32. And so we just needed to calculate 81 as our fourth, as our 51 to the fourth mod 55, so to speak, so that we can simplify that, or so that we can use that to go on to get our 8th and 16th power. And so because of that, we needed to calculate it, but we don't actually input it into our final calculation because we're only using the binary number 1, 2, 8, and 16 and not that 4th power. So we take our result, which was 52, 9, 16, and 36. And so yeah, this 81 turns into the 26, and so that's why we're not using it. And so whenever you multiply this out and take that to mod 55, that becomes 13. And of course 13 up here is in. So we decrypted the 52 to be 13, which using our table gives us in. So that one went well. The next one this one's a little, quite a bit more simpler. Because 1 to the 27th is just 1, it's fairly simple. 1 mod 55 just continues to be 1, and so 1 becomes A, just like we would expect from our previous encryption. So the next one continues similar to that of the 52. We have 25 to the 27th power, which is too large to compute. So we need to break it down into the binary powers again. So again, we take that to the first power, which goes to the 25th. 25 mod 55 just stays 25. Then we do squared, which becomes 625. 625 mod 20 becomes 20. The 20 squared becomes 400, and then we take 400 mod 55, and that equals 15. Then we use that 15 squared to become 225, and then we take 225 mod 55 to be 5, and then we take that squared, which is 25, mod 55 is 25. So it kind of loops back, which I thought was interesting. So the 25 to the 27th power, mod 55, becomes 25 times 20 times 5 times 25. And again, we're leaving that 15 out because it's the 4th power, and we're only looking for the binary 1, 2, 8, and 16. So this turns out to equal 20 at the end of the mod, which again is what we would expect, and t equals 20. Last one is similar to those of the M and T. So 17 is our ciphertext, right, that we're decrypting. And again, 17 to the 27th power is much too large for, your standard calculator or to do by hand. So we break it down into this more clever form. And we go through the steps. 17 mod 55 is 17 again. The squared becomes 289 mod 55, which is 14. Then we take that squared, which is 196 mod 55, which is 31. The 31 squared becomes 961, and the 961 mod 55 becomes 26, and that continues on down the line, giving us 16 as our final 17th to the 16th mod 55. And so this breaks down 17 to the 27th, mod 55 becomes this guy. And after doing the multiplication and doing it mod 55, that becomes 8. Which 8, when we look back up here, is h. So just like we would expect, the 52, 1, 25, and 17 becomes math, just like we started with. So as you can see, the decryption is quite a bit more complicated. It relies on some more difficult math, but as you can see, it's fairly interesting, at least to me. And so there are a lot of applications to RSA cryptography. For one, it's used a lot in privacy. So, for example, online games like Minecraft. Um, it protects your login and your personal info. A lot of texting apps like WhatsApp and Signal use RSA cryptography to keep messages private. Online shopping and banking use secure credit cards and passwords on websites. So HTTPS, that on the top of your browser, that is actually a lot of those security protocols use RSA cryptography. And then it's used a lot in ethical hacking and cybersecurity. And then, of course, quantum computing threats. RSA might be broken by future quantum tech when math meets sci-fi. And so, in conclusion, RSA is I would say very important. It's a powerful way to protect secrets with math. It's used in texting and online banking. It's very useful for privacy and things like that for keeping everything secure. And understanding RSA shows how math shapes the digital world. I think this is really cool because how often do we use texting, online banking, websites? They're all protected by this RSA cryptography method. And I think that's so cool that so many things in our real life world that we don't even notice it are based off of these cool aspects of math. And so, yeah, seeing how one aspect like RSA shapes the digital world, I think that's really cool to show and to see how math is in our day-to-day lives. And as tech evolves, RSA is going to continue to be a key piece of cybersecurity. And at the end of the day, math isn't just numbers, it's power, privacy, and the future. And RSA shows us that, and I think that's cool. So that's all I have. I hope you guys have enjoyed, and we'll see you all next time.